Hello everybody. So I will talk about role of tensor operators in explaining RK and RK star anomalies. This work is done in collaboration with Deeptimoy and Devjyoti, and it's based on this. So first two slides will be repetition. So recently LHCb has announced the anomaly in RK star in two bins, central and low bins. So, and these are respectively 2.2 to 2.2 and 2.4 sigma deviations. So, the quantity RK star is defined as ratio of two branching and branching of decays, and decays are BD going to K star mu plus mu minus over BD going to K star E plus E minus, and the beans are defined as in this way. So lower beans are the invariant mass of two leptons when they are in 0.045 to 1.1 electron GB square, and the central bean is from 1.1 to 6 GB square. So LS has another result on RK, and its significance is 2.5 sigma, and definition of this observable is similar to RK star, just BD will be replaced by B plus and K will be K plus. Okay. So we will further impose these inclusive constraints to constrain our Wilson coefficients. All the process I will discuss here involves B2 S transition. So, and effective Hamiltonian for this process was worked out by Mishiak et al., and it has this form. So, first 1 to 6 operators has some form. I have not writing this one, these things, and other dimension 6 operator on which we are interested in are these. So first operator is a photonic dipole operator, has universal contribution to modulo the lepton mass effects. Hence, it cannot explain the RK star anomalies, and it has also another constant from B to X S gamma. So to calculate the branching and etc. things, we need form factors, and these are taken from these two collaborations. Let me first try to explain the anomalies using only one tensor operators. So here you can see that red band corresponds to RK star central, and blue one is the lower, and also similar notation for lines. So you can see that this CT5E can bring down can explain RK star easily, and it for its value for plus minus 1, it can explain, it brings down its value to its central value. On the other hand, you can see the right panel where we plotted RK versus CT5E. So we see that it cannot bring down the standard model values down to the experimental allowed region. So CT5E cannot explain both the cases. So all the statement made for CT5E is applicable for CTE also. And another thing is that for mu1 case, if you change this delta CT mu from 0, then its effect is in opposite direction. So, so these operators cannot explain these anomalies. Now let's move to the combination. One is the vector, one is tensor, and here I'm considering C9e and C5e. So in the left panel, so blue region is for RK log, then red is blue region in orchestral lobe, red is orchestral central, and the green yellow is the RK. So, and this black region is the overlap of all the allowed region. So we can see that these two black regions are separated. So if we assume that delta CT5E is equal to 0, then it cannot explain the experimental result, and so CT5 C9E alone cannot explain this. In the right panel, so we impose the inclusive constraints and superimpose the overlap region of the previous one, and we can see that there is some overlap. So there is some region where all the anomalies can be explained. Okay. Here, instead of election, we are considering mu1. So convention color coding is similar to the earlier one. You can see that in the right panel, the allowed black region is in tension with experimental data, so simultaneous explanation is in tension. Now we consider delta C9E equal to delta 10E, or E goes to E will be changed to mu1, and so there is 4 pieces. So you can see that mu1 case is still in tension, whereas electron case is there is some region in electron case which can explain all these anomalies. And one more important thing is that you can see that gap between two black regions are reduced. So the role of tensor operator is reduced. In earlier plots, this gap was large. Similar comments can be made on primed operators. So in primed operators, mu1 sector cannot explain, and electron sector can explain. So we have used tensor operators, but tensor operators are not generated in dimension 6. So there can be some dimensionate operators. These are the list. These are some of the list. Okay. So first one is very hard to obtain because you have to integrate out some tensor things. Whereas second one is more common, and by fusing second one we can obtain tensor operators. And one interesting thing is that in second case they satisfy some relation. So considering this relation, okay, so we scan this and you can see that now the black region is around 3, whereas for CS and CP prime, and whereas for tensor case it is 1. So they are all approximately satisfying this relation. Experimentally allowed regions are approximately satisfy these regions. However, this Large value for the delta CS prime, CP prime, requires very low state. And another reason, constraint is that this large value is cannot explain PS to E